Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Our story begins not with an explosion, but with a slow cosmic death. 5 billion years from now, our Sun, the G-type main sequence star that has faithfully illuminated Earth since its formation, will begin its transformation into a red giant. This isn't speculative fiction. It's the well-documented stellar evolution that awaits all stars of similar mass. The Sun currently fuses hydrogen into helium in its core, maintaining a delicate equilibrium between gravitational collapse and radiation pressure. But this balance is temporary on cosmic timescales. As hydrogen in the core depletes, the fusion zone will migrate outward, causing the Sun to brighten by approximately 10% every billion years. Long before the red giant phase, Earth's oceans will evaporate as temperatures rise to over 100 degrees Celsius globally. The water vapor will act as a greenhouse gas, accelerating heating in a runaway process that will render our planet uninhabitable to complex life within the next 1 to 2 billion years. Recent models from stellar physicists indicate that by the time the Sun enters its subgiant phase 4 billion years from now, Earth's surface temperature will exceed 500 degrees Celsius, hot enough to melt lead. The atmosphere we breathe today will be replaced by a dense shroud of carbon dioxide, nitrogen and water vapor. Any remaining oceans will become supercritical fluids, neither fully liquid nor gas. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. As the Sun's core hydrogen exhausts around the 5 billion year mark, gravitational forces will compress the core, raising temperatures enough to ignite shell hydrogen fusion. The outer layers will expand dramatically, and our once familiar star will swell to hundreds of times its current diameter. During this expansion, Mercury and Venus will certainly be engulfed. Earth's fate, however, remains less certain. The Sun will lose approximately 30% of its mass during this phase through solar winds, weakening its gravitational pull. This mass loss will cause planetary orbits to widen. Earth's orbit may expand by as much as 50%, potentially allowing it to escape direct engulfment. But even if Earth avoids being swallowed, its proximity to the enlarged solar surface will subject it to temperatures exceeding 2,000 degrees Celsius, far beyond the melting point of rock. The final stage of the Sun's red giant phase will last a mere few hundred million years. The helium ash in the core will ignite in a helium flash, and the Sun will briefly shrink before expanding to its maximum radius. For several million years, it will fuse helium into carbon and oxygen in its core while continuing to fuse hydrogen in a shell around that core. Calculations suggest the Sun's maximum radius will extend to approximately 1 astronomical unit, precisely Earth's current orbital distance. By this point, Earth's surface will be completely transformed. Any remaining atmosphere will have been stripped away by intense solar radiation. The lithosphere, Earth's rigid outer shell, will partially melt, creating a global magma ocean reminiscent of Earth's earliest days, 4.5 billion years. The planet that once sustained forests, oceans, and civilizations will become a barren, molten sphere, orbiting at the periphery of an unrecognizable solar system. After the tumultuous red giant phase, the Sun will undergo a metamorphosis unlike anything humans have ever witnessed. Unable to fuse elements heavier than helium due to its modest mass, our star will never experience the spectacular supernova that ends the lives of more massive stars. Instead, it will shed its outer layers, creating a short-lived planetary nebula, a shell of glowing gas expanding outward at speeds of 20,000 kilometers per second. At the center of this nebula will remain the Sun's exposed core, a white dwarf. This remnant will be approximately the size of Earth, but contain about 50 to 60% of the Sun's original mass. Its density will be staggering. A teaspoonful would weigh approximately 15 tons on Earth. The surface temperature of this newborn white dwarf will exceed 100,000 degrees Kelvin, making it one of the hottest objects in the galaxy, despite having no ongoing fusion reactions. Earth, if it survives the red giant phase, will now orbit a white dwarf at a distance of roughly 1.5 astronomical units. From Earth's surface, now cooled to a solid blackened crust, the white dwarf sun would appear as an intensely bright bluish-white pinpoint, rather than the familiar yellow disk we see today. Despite its high temperature, the white dwarf's small surface area means it will emit only a fraction of the sun's current luminosity. The most extraordinary aspect of this new configuration is its stability. White dwarfs cool extremely slowly, maintained only by the residual thermal energy of their compressed particles. According to calculations from white dwarf cooling models, it would take approximately 1 trillion years for our sun's white dwarf remnant to cool to temperatures below the freezing point of water. During this extended cooling period, Earth would gradually refrigerate. Any remaining atmosphere would freeze onto the surface, creating thin layers of exotic ices. Water ice would be followed by solidified carbon dioxide, then nitrogen, oxygen, and eventually even the noble gases would condense. The planet's surface would be coated with these complex layers of different ices, creating a geological record of atmospheric composition. Remarkably, Earth's interior heat would persist for billions of years after the sun's transformation. The radioactive decay of elements like uranium, thorium, and potassium would continue to generate geothermal energy deep within Earth's mantle and core. This internal heating would create a habitable zone beneath the frozen surface, potentially containing liquid water in subsurface oceans. According to recent calculations published in the Astrophysical Journal, these subsurface oceans might persist for billions of years, maintained by the balance between geothermal heating from below and the insulating effect of the frozen surface above. This creates the tantalizing possibility that microbial life, perhaps descendants of Earth's extremophiles, could survive in these protected environments long after the sun's death. On the surface, Earth would be bathed in the faint glow of the white dwarf, supplemented by the light of distant stars. Without atmospheric interference, the night sky would be perpetually visible, displaying the Milky Way with unprecedented clarity. The very concept of day and night would fade as Earth's rotation gradually slows due to tidal interactions with other bodies in the solar system. As trillions of years pass, the white dwarf remnant of our sun will continue its gradual cooling process. Its intense blue-white glow will slowly shift through the spectrum, from white to yellow, then orange, and finally a dim reddish hue before fading to invisibility. After approximately 10 trillion years, the temperature will fall below 100 degrees Kelvin, and the former sun will enter its final evolutionary stage, a black dwarf. This term, black dwarf, is somewhat misleading, as these objects aren't truly black in the sense of absorbing all light. Rather, they emit so little electromagnetic radiation that they become effectively invisible to optical observation. A black dwarf is essentially a white dwarf that has exhausted its thermal energy, a cold crystalline sphere of electron degenerate matter, primarily carbon and oxygen, with trace amounts of heavier elements. Earth's orbit during this phase will be remarkably stable. Orbital calculations demonstrate that without the disruptive influence of solar winds, radiation pressure, or significant mass loss, a planet can maintain its orbit around a stellar remnant for timescales approaching 100 trillion years. Tidal forces will have long since locked Earth's rotation to match its orbital period, meaning one side would perpetually face the invisible black dwarf while the other would face the galaxy. The planet itself will have undergone profound transformations. The once molten core will have solidified completely as radioactive elements exhaust their decay energy. The last vestiges of Earth's internal heat will dissipate into space, leaving the planet in perfect thermodynamic equilibrium with the cosmic microwave background radiation, which by this epoch will have cooled to mere fractions of a degree above absolute zero. Most remarkably, the fundamental chemical composition of Earth's surface will begin to change through quantum tunneling effects. At these extreme timescales and low temperatures, even seemingly impossible chemical reactions become feasible as atoms occasionally tunnel through energy barriers. Over periods of 10 to the power of 100 years, the surface materials would gradually transform into their most energetically favorable configurations. Recent theoretical work by physicists suggests that in this ultimate frozen state, Earth would become increasingly homogeneous. The distinct layers that characterized our planet throughout its history, core, mantle, crust, would gradually erode as atoms redistribute themselves through quantum processes. The entire planet would slowly progress toward a uniform crystal lattice structure. Any record of life having existed on Earth would be extraordinarily well preserved in this environment. Without erosion, volcanic activity, or plate tectonics, surface features would remain virtually unchanged. Footprints left by the last organisms to walk the surface might remain pristine for trillions of years, though altered at the atomic level by the same quantum processes affecting the entire planet. The relationship between Earth and its stellar remnant would enter a surprising new phase during this era. As both bodies cool to temperatures approaching absolute zero, an unusual phenomenon called quantum entanglement begins to manifest at macroscopic scales. Theoretical models suggest that over sufficiently long timescales, quantum coherence could develop between Earth and the black dwarf, creating subtle but measurable correlations in their physical properties. Strangely, Earth might outlast the very atoms that comprise it. Current models of proton decay suggest that after 10 to the power of 40 years, baryonic matter, the conventional matter that makes up planets and stars, may begin to decay into radiation. If these models are correct, Earth would gradually dissolve into a diffuse cloud of elementary particles, bringing a true end to the physical planet, approximately 1,000 trillion years after the Sun's initial death. Not all potential futures for Earth involve it remaining in orbit around the Sun's remnant. Astronomers have identified several mechanisms that could eject Earth entirely from the solar system, transforming it into what scientists call a rogue planet, a planetary body that wanders the galaxy unbound to any star. The most likely ejection scenario would occur during the Sun's white dwarf phase. As the solar system ages, subtle gravitational interactions between the remaining planets accumulate over billions of years. Computer simulations run at the Harvard-Smithsonian Center for Astrophysics suggest approximately a 2% chance that these interactions could amplify into orbital resonances powerful enough to dramatically alter Earth's trajectory. If Mercury or Venus survive the red giant phase, which current models suggest is unlikely, they would be particularly susceptible to these instabilities. Their destabilized orbits could, in turn, perturb Earth's path through a gravitational slingshot effect. A close encounter with Jupiter or Saturn could provide the final push needed to exceed the solar system's escape velocity. Once ejected, Earth would enter the vast interstellar medium. Without stellar radiation, surface temperatures would plummet rapidly to approximately minus 240 degrees Celsius, with only the planet's residual geothermal energy preventing temperatures from reaching absolute zero. The atmosphere would condense onto the surface in reverse order of freezing points, first water vapor, then carbon dioxide, and finally nitrogen and oxygen, creating a layered frozen shell. Remarkably, this frozen state might preserve Earth's potential for habitability. The thick ice shell would act as an insulator, trapping geothermal heat from radioactive decay in the planet's interior. Recent studies published in the International Journal of Astrobiology suggest that subsurface oceans could persist in rogue planets for billions of years, maintained by this internal heating. Evidence for this possibility comes from observations of moons in our own solar system. Jupiter's moon Europa and Saturn's moon Enceladus both harbor liquid water oceans beneath ice shells, heated primarily by tidal forces. A rogue Earth would lack tidal heating, but would compensate with greater radioactive elements in its core and mantle, potentially sustaining liquid water zones for billions of years after ejection. These subsurface environments could harbor extraordinary ecosystems. Microorganisms might evolve to exploit chemical energy rather than sunlight, similar to chemosynthetic communities found near Earth's deep-sea hydrothermal vents today. If more complex life survived the transition, it might adapt to navigate the eternal darkness using bioluminescence or other sensory adaptations. As a rogue planet, Earth would travel through diverse regions of the Milky Way. During its journey, Spanning tens of billions of years, it would encounter varying concentrations of interstellar gas and dust, occasionally passing through star-forming regions, spiral arms, and the galactic halo. Each environment would subtly affect the planet's trajectory through gravitational interactions. The most dramatic possibility during this wandering phase would be a close encounter with another star system. Astronomers estimate that a rogue Earth would pass within 1 light-year of another star, approximately once every 100 million years. During these encounters, Earth could potentially be captured into orbit around the new star, if the relative velocities and approach angles fell within specific parameters. If such a capture occurred, Earth would experience a second dawn as stellar radiation once again reached its surface. The frozen atmospheric gases would gradually sublimate, potentially creating a new transient atmosphere. While this atmosphere would bear little chemical resemblance to Earth's original life-supporting envelope, it would temporarily shield the surface from cosmic radiation and provide pressure necessary for liquid water to exist if temperatures rose sufficiently. As a rogue planet drifting through interstellar space, Earth would experience an environment utterly unlike anything in its previous existence. No longer bathed in the consistent radiation of a parent star, it would instead encounter the diverse and often sparse conditions of the interstellar medium. This vast space between stars is not empty, but filled with extremely low-density hydrogen and helium, interspersed with occasional molecular clouds, cosmic rays, and the omnipresent bath of microwave background radiation. Earth's interaction with this medium would gradually reshape its outer layers. As it moves through space at velocities potentially exceeding 50 kilometers per second, the planet would encounter interstellar particles that would slowly erode its frozen surface through a process similar to cosmic sandblasting. Over billions of years, this erosion could remove several meters of surface material, particularly from the leading hemisphere, creating a subtle but measurable asymmetry in the planet's shape. Without a protective magnetosphere, which would have ceased when Earth's core solidified, high-energy particles from galactic cosmic rays would penetrate the surface ice, triggering nuclear reactions that would produce exotic isotopes. Scientists studying such worlds would look for elevated levels of beryllium-10, aluminum-26, and other cosmogenic nuclides as telltale signatures of a planet's interstellar journey. The deep cold of interstellar space would also drive unique chemical processes. At temperatures approaching absolute zero, chemical reactions proceed through quantum tunneling rather than thermal activation. Recent laboratory experiments with ultra-cold atoms have demonstrated that complex organic molecules can form under these conditions through mechanisms fundamentally different from those in warmer environments. Earth might accumulate a thin veneer of new material during this phase. When passing through dense molecular clouds, the nurseries of future star systems, the planet could accrete a coating of complex organic compounds, water ice, and other volatiles. These materials, ironically, are similar to the primordial ingredients from which Earth initially formed nearly 10 billion years earlier. Perhaps most significantly, Earth's trajectory through the galaxy would be influenced by the galaxy itself. The Milky Way's spiral structure represents density waves of stars and gas rotating more slowly than the individual stellar components. As Earth passes through these density waves approximately once every 200 million years, its path would be slightly altered by the collective gravitational influence of billions of stars. Mathematical models suggest that after approximately 5 billion years as a rogue planet, Earth would have a 30% probability of migrating to the galactic halo, a region of significantly lower stellar density. This would drastically reduce the likelihood of stellar encounters, potentially allowing Earth to preserve its frozen state for trillions of years with minimal external disturbance. During this extended solitary journey, Earth would occasionally pass through the scattered debris of destroyed planetary systems. Stellar evolution is often catastrophic for planets. When stars like the Sun exhaust their hydrogen fuel and expand into red giants, they can completely vaporize their inner planets. This process liberates substantial quantities of heavy elements into interstellar space, creating diffuse clouds of material that was once part of worlds potentially similar to Earth. When passing through such regions, Earth might accrete small amounts of this material, atoms and molecules that once belonged to other planets, potentially including worlds that harbored life. In this way, a rogue Earth would become a repository not just of its own evolutionary history, but potentially of multiple planetary histories spanning billions of years of galactic evolution. If intelligent life had ever existed elsewhere in the galaxy and transmitted electromagnetic signals, these waves would continue propagating through space long after their civilization had vanished. As a rogue Earth drifted through the galaxy, it would pass through countless overlapping spheres of ancient transmissions, a silent witness to the electromagnetic echoes of civilizations it would never otherwise encounter. Over timescales spanning hundreds of billions of years, the probability of extraordinary events transitions from infinitesimal to inevitable. For a rogue Earth wandering the galaxy, one such possibility is a close encounter with another planetary system. Astronomers have calculated that such encounters occur approximately once every 100 million years, with the vast majority being distant and inconsequential. However, approximately once every 10 billion years, a wandering planet might pass, close enough to be gravitationally captured by another star. If Earth were captured into orbit around a new star, the consequences would be profound. The star's mass, age, and spectral type would determine Earth's fate. Capture by a massive O-type or B-type star would be fleeting, as these stars live only a few million years before exploding as supernovae. Capture by a long-lived red dwarf, however, could provide a stable environment for tens or even hundreds of billions of years. The orbital parameters following capture would be essentially random. Earth might find itself in a highly eccentric orbit, experiencing extreme temperature variations as it alternates between close approaches and distant apoapsis. Alternatively, it could settle into a relatively circular orbit, potentially within the star's habitable zone, the region where temperatures allow for liquid water on a planetary surface. If Earth were captured into a habitable orbit, its frozen atmosphere would begin to sublimate. Nitrogen and oxygen would return to gaseous form first, followed by carbon dioxide. Water would melt more gradually, first at the equator and then advancing toward the poles. The thawing process could take thousands of years, creating a planet-spanning hydrological cycle for the first time in billions of years. More remarkable still is the possibility that dormant microorganisms might survive this entire sequence. Experiments conducted at the European Space Agency have demonstrated that certain bacteria can survive in suspended animation for extraordinary periods when frozen in ice. If similar organisms existed on Earth prior to its freezing, they might remain viable in deep subsurface pockets, protected from cosmic radiation by kilometers of ice and rock. Upon thawing, these ancient microbes could potentially recolonize the planet's surface, initiating a second genesis, billions of years after the first. The organisms that would thrive in this environment would likely be extremophiles, species adapted to harsh conditions, similar to the archaebacteria found in Earth's most inhospitable environments today. Another possibility is that Earth might be captured into a system already harboring life. If microorganisms from that system reached Earth through panspermia, the transfer of life between celestial bodies via meteorites, they would encounter a planet with a complex chemical history, but devoid of competing organisms. This scenario would represent a unique natural experiment in evolutionary biology, as organisms adapted to one planet's evolutionary history colonize another with an entirely different geological and chemical background. Even without capture, close encounters with other planetary systems could dramatically alter Earth's trajectory. A near miss with a massive star could accelerate Earth to velocities approaching 1,000 kilometers per second through gravitational slingshot effects, potentially sending it into intergalactic space. Current models suggest approximately a 1% chance of ejection from the Milky Way over a 100 billion-year timescale. If ejected into intergalactic space, Earth would experience an environment even more sparse than the interstellar medium. The density of matter in intergalactic voids is approximately 1 atom per cubic meter, a near-perfect vacuum. In this environment, Earth would be subjected to even less erosion, potentially preserving its surface features for trillions of years with minimal alteration. Throughout these vast timescales, Earth would bear witness to the ongoing evolution of the Milky Way itself. Our galaxy is on a collision course with the Andromeda Galaxy, with the merger expected to begin approximately 4.5 billion years from now. The resulting elliptical galaxy, sometimes called Milkomeda by astronomers, would have a radically different structure than either progenitor galaxy, potentially altering the frequency of close stellar encounters and other events that could affect Earth's trajectory. The final chapter of Earth's story unfolds against the backdrop of an aging universe. Current cosmological models indicate that approximately 100 trillion years from now, star formation will cease throughout the cosmos as the supply of free hydrogen becomes exhausted. The majestic spiral galaxies that dominated the universe's middle age will fade as their constituent stars die one by one, leaving behind white dwarfs, neutron stars, and black holes. By this era, if Earth has remained intact, whether orbiting, the Sun's black dwarf remnant, or wandering interstellar space, it will have witnessed the entire stellar epoch of the universe. The night sky, once brilliant with stars, would grow increasingly dim. The familiar constellations would gradually disappear as stars exhaust their nuclear fuel and fade from visibility. By the time 1 quadrillion years have passed, the universe will be approximately 100,000 times darker than it is today. The fate of matter itself becomes uncertain on these extreme timescales. According to the standard model of particle physics, protons, the building blocks of atomic nuclei, may be unstable with a half-life exceeding 10 to the power of 34 years. If this theory is correct, Earth's atoms would gradually decay through processes like proton decay, where protons convert into positrons and neutral pions. This decay would occur at the subatomic level throughout the planet's volume. Initially imperceptible over unfathomable spans of time, approximately 10 to the power of 40 years, this process would reduce Earth to a diffuse cloud of elementary particles and radiation. The planet that witnessed the birth and death of countless stars would ultimately share the universe's fate of gradual dissolution. Before this final dissolution, Earth would likely experience one last transformation. As the universe continues its accelerating expansion, driven by dark energy, galaxies beyond our local group will recede beyond the cosmic horizon. Eventually, even nearby galaxies will disappear from view as the expansion carries them beyond the observable universe. Earth, whether within the remnant of the Milky Way or drifting through intergalactic space, would find itself in a cosmos growing increasingly empty and dark. Quantum effects, negligible on human timescales, become dominant. In this far future, quantum tunneling would allow occasional particles to overcome seemingly insurmountable energy barriers. Over periods exceeding 10 to the power of 100 years, even the most stable structures would be subject to quantum fluctuations that could dramatically alter their composition and configuration. During this quantum era, black holes would dominate the universe's evolution. Through the process of Hawking radiation, these objects would slowly evaporate, converting their mass into radiation. The smallest black holes would disappear first, while supermassive black holes might persist for up to 10 to the power of 100 years. These evaporating black holes would provide the final sources of energy in an otherwise cold and dark cosmos. If Earth were orbiting one of these black holes, perhaps having been captured during a close encounter in the distant past, it might experience one final moment of warmth as the black hole entered the final stages of evaporation. The Hawking radiation would briefly increase to incredible intensity before the black hole disappeared entirely, potentially melting Earth's frozen surface for a fleeting moment after trillions of years of darkness. In the most extreme future, scenarios quantum fluctuations might produce remarkable events. According to quantum field theory, there exists a non-zero probability that Earth or its remaining subatomic components could spontaneously tunnel into different configurations or states. These fluctuations could potentially reorganize matter into complex structures, creating brief moments of order in an otherwise entropic universe. The most speculative theories suggest that in an eternal universe given infinite time, quantum fluctuations could eventually reassemble Earth's components into configurations resembling the original planet. The probability of such an event is unimaginably small, approximately 1 divided by 10 to the power of 10 to the power of 70. Yet in an infinite timeline, even the most improbable events would eventually occur. This raises a profound question. In a universe where information is conserved at the quantum level, does Earth's structure, and by extension the information encoding its history and evolution, persist in some form indefinitely? The answer lies at the intersection of quantum mechanics, information theory, and cosmology, fields that continue to evolve as we deepen our understanding of the universe's fundamental nature.